this video, we're going to cover repeated measures, designs with interactions. So a doubly repeated design is sometimes what it's called, or any type of factorial ANOVA where everything is repeated. Sometimes these are called profile analysis. We have lots of repeated measures put together in the same one, but we're going to analyze this as if it's just a factorial ANOVA. Okay. So the data set I have open is our two-way repeated measures ANOVA, and it's actually also going to be used for the mixed design. So we're going to get rid of some of the variables here just to show you just the ones we need. Okay, so I'm going to delete these last two because that's part of another example, and then this first one labeled group, and I can leave in the subject number, or if it's going to confuse me, I can delete it. Let me save this as something else so I don't overwrite my original file. There you go. Okay, so what you need for this data is the 4 columns. And so what's going on? Well, what we have is a 2x2 repeated measures ANOVA. So I have 2 levels of one variable and 2 levels of another variable. Let's open Word here and I'll kind of show you how this design works. So I have 2 variables here by 2. So the first one, the overall independent measure, is forward strength. So forward strength is how much 2 words have in common. If I give you cheddar, how many people out of 100 would say cheese? So it's very similar to Family Feud, where they ask people what are the most common words that people would say. If I gave you cheddar, cheese is one of the biggest ones. And so that's how strong the relationship is forward. So if I tell you this word, how many people out of 100 would say that next word? And so forward strength, so this is forward strength out here, has 2 levels. It is either going to be low, so we set it to some word pairs that don't have a very high strength, excuse me, and then we set it to high, where some pairs do have a very high forward strength. So steak to sirloin is a really high forward strength. Lost to found is a really high forward strength. And a good example of low might be cheese to cheddar, because most people say mouse to cheese. And then in my second variable here, I have a table that will not let me resize. Let's move it over. Oh, fine. The second variable over here is backward strength. I'll just write it down here. Backward strength is how much the variable varies the other way. So if I have lost to found, I've told you that forward strength is really high, but found to lost also has a very high backward strength. So this is how many times out of 100 if I gave people the second word would the first word pop out. And so that's not always, it's not the same forwards and backwards. So I can give things that are low, like sirloin to steak has a very high forward strength. If I said steak first, most people say sauce. So sirloin is very low backward strength. And then we have things that can be high. So sister, brother is pretty high in forwards and backwards. On, off is a pretty high one in both directions as well. Okay. So what we've done is we're getting people to estimate the likelihood of events, and we're varying how much they are related going forwards and going backwards. And our point in the study was to try to show that both variables matter. So there should be an interaction between forwards and backwards strength to predict their ratings. So that creates me 4 groups: a low low, a low high, a high low, and a high high. Either way I want to label it, I label going across just then. So I have 4 conditions, and that's a 2x2 repeated measures only ANOVA. And so everyone got all 4 types. So the setup I have here in SPSS is that since everyone is in all 4 boxes, I have to put it in with 1 column for each condition. Now, normally we have one column for each DV, but repeated measures is sort of weird in SPSS where you have to treat the columns as DVs and IVs together at the same time. And so the IV is sort of here at the top, and then the DVs are the numbers within. And so I've got my 4 conditions just labeled out. And what I could do is over here in the label and make that a little more useful. So I could say this is forward strength. Get SPSS to play along here. Forward strength is low, BSG is low, and then I have forward strength is high, BSG is low, and so that would be that first row, and then I have forward strength is low, BSG is high, and forward strength is high, BSG is high. So I have all 4 combinations. Okay, and those labels will help me here in a little bit. So let's go to G power. So how many subjects do I need in my study? Okay. First thing I'm going to do is change this to F test. And then here under statistical tests, we're going to pick the repeated one. So it's labeled as ANOVA, repeated measures within factors. So that's repeated and repeated. Under input parameters here, I could click determine to figure out my effect size from eta squared or partial eta squared, which I will get in my output, or I could leave it alone. But since I know that I have a big effect size on this kind of data, because I've done it before, because this is research that I do all the time, the interaction effect size was 0.31. And I'm going to hit calculate and transfer to main. Okay, so this is something you'd have to have from previous research or estimate. So I've got a big effect size F. I'm going to leave alpha as 0.05. And here under power, I'm going to change that to 80% because that's the standard that we like to use. Under number of groups, I'm going to put the number of IVs. Okay, so that's 2. And the number of measurements here actually is 4. So I'm not changing these because it matches what I've already plugged in. So number of measurements is the number of conditions or the number of levels. Correlation among repeated measures is going to be the lowest estimate of the correlation between conditions. So I could really quickly run a bivariate correlation to determine what those are. So let's try that. So we're going to analyze, correlate, bivariate. Plug in all 4 of those and hit OK. And then I would pick the lowest correlation out of those time points. So 0.618. And so this is supposed to be an estimate of how much each of the conditions are related to each other, and you lose power in repeated measures if the correlations are low. You want people's scores to be consistent over time. Now they might be going up or they might be going down, but you want everybody going up and everybody going down. So I don't mean consistent like I'm going to score a 5 each time. I mean consistent in that everybody is changing in the same direction. And so the correlation here, you can estimate it as 0.5 to 0.7 is pretty standard. 0.5 is, I'm not sure. If you want to be super conservative and estimate more people, lower that number. The non-sporosity correction is epsilon from Mockley's test. And so you probably won't really know that number beforehand. If you have a previous study to estimate it from, you can change it. Let's hit calculate. And so it says I need 6 people. Okay, now 6 people who have taken all 4 conditions, but still, only 6. Had this been a between subjects design, that would have been much higher. So this is how you have more power, because between subjects that at minimum would have been 6 in each group, which would have been a 24, but the total sample size here is only 6, because I have a big effect size. Let's close that. Now, to run this test, we're going to start, I'm on page 136, by screening for accuracy and missing data. So I have got the data open and I want to go Analyze, Descriptives, and then Frequencies. I'm going to move over all 4 of them. Under Statistics, definitely mean, standard deviation, but min and max is really where it's at to tell me if my data is out of range. I can also pick skew and kurtosis just to kind of look at it now, but that might change later if I find some outliers. Hit continue. I'm going to turn off the frequency tables. These are all continuous data. Those tables would be huge. And then OK. So what it tells me down here is that my average scores are 50, 64, 55, 77. That's what I would have expected. I actually don't have any missing data, which is nice. The standard deviations are wildly consistent, which is super nice because remember you want them to be pretty much the same to meet homogeneity. And then I don't appear to have anything too crazy going on. The lowest value is 20, the highest value is 80, 90, 93, so these scores are what I would have expected. And the range of the data from this experiment would have been 0 to 100. So what's the likelihood? How many people out of 100 would give me that second word? So I can't go over 100 and I can't get negative. So I don't appear to have any accuracy issues, and I don't appear to have any missing data. And it kind of looks like a lot of the other things are going to be good for me too. Like a skew is almost, it's close to 0. Kurtosis is not too bad. Remember 3 is the cutoff score for those. So I'm doing pretty good so far. The next thing I'm going to do is check for, I could look at univariate outliers. So let's go Analyze, Descriptives, and then Descriptives. Move over all 4. And then hit Save Standardized Values as Variables. That'll give me the z-score. Okay. Right? And so now, in the data set, I have all 4 of these as z-scores. Now I could right-click and sort and do all that stuff, but what I'm going to do is show you a shortcut. Analyze, Descriptives, and then I like frequencies the best, so let's go Frequencies. I'm going to move all 4 of these bad boys out, put in my 4 z-scores, and then under Statistics, I'm going to turn off a lot of these things because I've standardized them. So the mean and the standard deviation will be 0 and 1 because that's what the mean and standard deviation of z-scores are. I really want to look at the min and the max of my z-scores. Continue and OK. And then here I can tell if I have anything over 3. So 3 is the cutoff score for univariate outliers and z-scores. And I have some that are close, but the only one I seem to have problems with is this last one, so high, high. And it was negative, so I'm going to sort descending to put the, oops, just kidding, ascending to put the negatives at the top. And I have 2 univariate outliers. Okay. So their scores are way below normal because they're negative. And that's because they're supposed to be rating these numbers really high. So an FSG high condition, if people were perfectly good at this task, because there are real numbers for this, they'd be picking about 80. And they're picking 30, so that kind of puts them way below normal. But I don't want to delete anybody based on univariate outliers alone. So I am going to test multivariate outliers. So let's go transform, compute. I'm going to call this variable random because I'm going to make myself a random variable. Under function group, hit R to get random numbers quickly. RV chi-square, and we love the number 7. So I'm going to hit OK. So I have my fake random variable because SPSS does not do this as a random variable. You get the same numbers each time. And then now I'm going to run my fake regression so I can look at Mahalanobis and then my other multivariate tests. So let's go Analyze, Regression, Linear. Put my random score in the dependence box and my 4 conditions, don't use the z-scores, in the independence box. Under plots, z, pred, and y, z, residual, and x, histogram, and the normal probability plot. And then under save, Mahalanobis. And okay. It's going to give me a bunch of output, but I'm going to go back to the data. I'm going to sort this descending. And then I'm going to go to a chi-square table to figure out if I have any outliers. So how many degrees of freedom should I use? Well, I have 4 levels, and I put all 4 of them into, 4 conditions, and I put all 4 of them into the independent variable box, so I'm going to use 4. That makes my cutoff score 18.47, so 0.001 with 4 degrees of freedom, 18.47. And that means I have one person whose score is an outlier. And it's interesting because that outlier person, based on a multivariate combination, is not the same person that we figured out a minute ago. So they're the next person down, and then this one as well. But you'll see that they don't always agree. They usually agree, but they don't always agree. So these 2 scores are outliers in a univariate fashion for this particular column, but multivariate, the pattern of people's scores, is very strange for this person. Now, for the rest of the how-to guide, I'm pretty sure I left them in, because while their scores are weird, they're legitimate. So I'm going to leave them in. They don't really make a huge difference. You could delete them, and if you ran this analysis with deleting them, the numbers would change just a little bit from what I have in the notes, but it doesn't change the overall pattern of the data. And in those sorts of cases where I test it with and without, and they don't really change the pattern of the data, I leave them in and say that in my results section. Okay, next step is multicollinearity, which we haven't had in a while. So analyze, correlate, bivariate. I've actually already done this, so it's going to be set up. All 4 of my conditions. Hit OK. And this really is to just make sure that the thing is going to run. You expect these to be highly correlated. That's the point of repeated measures. That saves you the trouble. It gives you more power. However, if they're correlated perfectly or like at 0.9999, it will not run. It will give you a Hessian matrix not definite error the last time I checked, or something to that effect, which essentially means that 2 of the columns are perfectly the same. And it just won't do anything with those because there's not enough variance to work with when they're exactly the same. And when that happens, I always tell people either eliminate one column or average them, because they're basically the same column anyway. So get rid of one of the columns or average them. But I've checked this correlation table out. We've got one that's at 0.89, but remember the rule here is much higher, so 0.99 or essentially 1. Okay, don't forget that these ones are it's correlated with itself. Those are supposed to be there. So no multicollinearity problems. I did not delete anybody, so I can use this output I already have. So let's look at linearity first. That looks pretty good. It's pretty close to the line, so I would say that the data is fairly linear. For normality, this looks pretty good too, except we got these 2 little dudes over here, or 3 little dudes over here. And those are probably our people who are univariate and multivariate outliers. But what I could do to check and figure out if this were really screwy is look at the univariate histograms. So let's get those. Analyze, descriptives, frequencies. We do frequencies so many times, right? So I need my 4 variables. I turned off display frequency tables and it gave me that warning that says I don't have any output. Thanks. Under statistics, let's get skew and kurtosis so that we can look at how much they lean and how skinny they are. And then under charts, histograms, and if you're not good at it, show normal curves. Continue, and OK. This should give me the 4 univariate graphs. I can look at skew and kurtosis, which I've actually already done at the top, but if you had deleted people, you would need to do this again. And nobody is skewed or too kurtotic, but you do have ones that are a little higher than the rest. No big deal. So this looks fine. This is slightly negatively skewed. That one looks fine. This one's a little more negatively skewed. And that is because they're supposed to be. So sometimes you got to think about what is the data that I'm working with. And in both of these conditions, FSG high, BSG low, and FSG high, BSG high, they're supposed to guess about 80. So really what's messing this up is part of it is the research design. People are supposed to guess high numbers. And then for the low variables, they're supposed to guess low numbers. So we should actually have some positively skewed data in here, but we are so bad at this task we don't. And so what's really messing it up are the people who are guessing the wrong direction. Okay, I'm pretty sure that's because everybody wrote like on these people, they wrote low numbers on all of them. Okay, so they're kind of, those are our outliers that we had a minute ago. So I don't appear to have any normality issues. The last one is homogeneity. There we go. Which is this fun little scatter plot. So across here at 0, this dot should be evenly spread. And then across here at 0, the dot should be evenly spread. And it's pretty close. Again, we have our 3 persons out here who are probably the same 3 persons out here. I could check it, but I think it's going to be okay because the dots are fairly even across. You won't get Levine's test on this one because there's no between subjects. So you just kind of have to look at this plot to tell if your variances are roughly similar, or you could look at the standard deviations for each time point. And we already did that, and I said they're astonishingly the same, because that never happens. That was at the very top. Okay, so I scrolled way up to the top. My standard deviations here, 12.6, 12.5, 12.6, 11.9. So that doesn't ever happen to me usually, so it's kind of nice. They're all the same. Okay, so let's run the analysis. This is the tricky part. So go analyze, GLM for general linear model, and repeated. So anytime you have any repeated components, it's under repeated. And here we're going to label this. It is so tempting to, at this point, I have 4 columns to put in 1 variable and write 4. Okay, and that will be incorrect. If you want to treat this as a factorial design where you have 2 levels of one variable and 2 levels of another variable, you have to enter that here as 2 separate variables, each with 2 levels. If you enter it as 1 variable with 4 levels, it will run a one-way ANOVA. If you're trying to do factorial or 2-way ANOVAs, you have to separate them out. So I'm going to do forward strength and tell them I have 2 levels. And then backward strength and I have 2 levels. And then hit define. Now here's the hard part. When you get to this screen, things have to match. So this is kind of tiny, but we've got FSG here and BSG, and this 1, 1, 2, 2, 1, 2 thing. So let me see if I can write that out to make that clearer what is going on. Okay, so it told me it does like this. First variable, second variable, and then it says 1, 1, 1, 2, 2, 1, 2, 2. Okay. And that's in the same order, FSG, comma, BSG. And so actually what it's doing is it's saying you should figure out how to map this box up here that we have drawn to these numbers here. So what I'm going to do is I'm going to give forward strength, the first one, a label. And since this has a direction where some of them are supposed to be low and some of them are supposed to be high, because remember the order matters, I'm going to label the first 2 low. And then the second 2 I'm going to label high. And that's for forward strength. Then the next thing I'm going to do is apply that same labeling to the second pair. So low, comma, high. I can type today. And then low, and then high. Okay. So now I should have all 4 of them labeled. And I have got 4 different combinations. So I haven't doubled up anywhere. Once you've figured that part out, now you can, now I can match them up here. So the first one I want FSG low, BSG low. So the first one here. And then the second one I want FSG low, BSG high. So that's actually not quite the order I have them in an SPSS. Let's do this. There we go. So I've got FSG low, BSG high, which is the second one down now. Then I need forward strength high, backward strength low, forward strength high, backward strength high. And so I have mapped the 1, 1, 1, 2 to my variables and their levels. You could do backward strength first. It does not really matter the order you put the variables in, but the order that the conditions go in does matter. All right, from there, let's do options. I'm going to move over all three and hit display means for. And then descriptives, effect size, and homogeneity. Now here for homogeneity, I don't actually need it because that's just Levine's test. But this is one of those things that I just am in the habit of clicking it because then when I do a mixed design, I don't forget to ask for it. The other thing we can do is here under compare main effects, I could get it to give me just the main effects. It won't do the interactions, but I could pick Bonferroni or Siddock-Bonferroni here to do the main effects for these variables. Now, that's what you can do. I'm not going to do it. Okay, why am I not going to do it? Well, this set of variables only has 2 levels. So forward strength is low and high, backward strength is low and high. And this button only does main effects. See, it says main effects. And so that is actually a waste of my time. It will give me a Bonferroni Posttalk table, but since there's only 2 levels, I don't need to do it. That's already covered by the ANOVA. So when I get the main effect for the ANOVA, it's the same thing as that Posttalk test. So I'm going to leave it off, but that's how you could do it if you had a 3x4 and you wanted to look at the main effects. Okay? SPSS never does interactions for you that I'm aware of, unless you do contrast coding. So you will always have to do the Posttalks for interactions by hand in some way. Okay, so for between subjects, that's split file and independent T. For repeated measures, what you'll see here, it's going to be dependent T. It's actually a little easier. Okay. From there, I continue. And then I could get some plots. We'll talk about why the plots are terrible for this design, for chart builder. But let's get some plots so we can see what's going on. So move forward strength on horizontal, backward strength on separate lines, and then hit add. And then if you aren't sure what you want to do, you can do the reverse and hit add so you just don't have to run the whole analysis again. Continue. And then that should be everything. If you'll notice, if you click Posttalk, you won't get anything because they are anti-repeated measures Posttalks. And then hit OK. Alright. Oops, sorry. I wanted to do it this way. First thing it did was give me a warning that I asked for homogeneity, and it won't do it. That's fine. So it just sort of told me, hey, dummy, there's no between subjects. I'm not going to run Levine's for you. Neat. The next thing it gives me is it tells me what I ran, so I can make sure here I have my 1, 1, 1, 2 stuff lined up. Hang on to this descriptives box. It will be super helpful for effect size, but it's not totally necessary because I have them down here as well. And this one has a standard deviation and n, but really n is the same in all of them, so that should be the same number in all 4. The multivariate test is for repeated measures ANOVA, so I'm going to get rid of that. I don't need it. And then sphericity. So we've talked about sphericity. It's about compound symmetry. So sphericity is that the correlations between 2 time points or 2 levels are the same, or the difference score variances are the same. Well, I have all zeros here. What happened? Well, you didn't do anything wrong. It's sort of hard to have correlations between level 1 and level 2, and level 2 and level 3 when there's only 2. And so you don't get any of Mauchly's test when there's only 2 levels of any particular variable, because there just isn't a way to have the correlation between time 1 and time 2, and then time 2 and time 3 when there's only 2 of them. Okay. So Mauchly's test on this one, useless. The next thing that happens is that I get my gigantic within subjects effects box. So this is where all the action is going down. And it looks different from all the ones we've covered, because it basically runs 3 little mini ANOVAs. And so you're going to look at each pair, FSG and error, BSG and error, FSG and BSG and error, separately. Because what happens in repeated measures ANOVA is that the errors are calculated separately. Because there are, in theory, 3 different sort of DV kind of things going on. It's not quite how it works, but that's the idea. Whereas when you have between subjects variables, there's only still 1 column for the DV, and you have multiple columns for the IV. And then here, in this sort of design, it calculates mean squared error separately for each one. So it gets parceled out across the different main effects and interactions. So that looks confusing, but basically that means I'm going to do each main effect and interaction separately, so it's not always going to have the same second error component. So let's do forward strength. We got our main effect over here. So I'm going to write F, and it's going to be 1 and 157. I'm pulling that from degrees of freedom and degrees of freedom. Anytime for Mauchly's test you have a square design, 2 by 2, 3 by 3, 4 by 4, not Mauchly's. Anytime you have a square design, the numbers here are going to be the same. Okay, so it'll be 1 and 157, 1 and 157, 1 and 157, and that only happens when the designs are square. So if you were to have a 3 by 4, you wouldn't see the same numbers over and over again. Okay, so if you get different numbers, you haven't done anything wrong. And so my first F is 965.99. P is less than 001. And partial eta squared is 0.86. Another quick note about if you decide to correct with Mauchly's, we didn't need to in this experiment, but if you did, use the same line going all the way across. So don't say that you used a Hunfeld correction and then give me the degrees of freedom for sporicity assumed. So be sure you're going all the way across with it. Otherwise, the numbers you're giving are incorrect. And on those, you'll see partial degrees of freedom because they're correcting. This one has no correction. That's why there are no, they're all the same. And what happened in this first one? So this main effect is significant. And it's covering 86% of the partial variance, which normally that will give you pause because that is a lot, right? So that's covering the vast majority of their scores, the difference between their scores. That's just crazy. In this particular study, it makes sense to me, though, because what we're trying to do is get people to guess the frequency of these events. So we have numbers that they're supposed to guess, they guess the numbers, and we're looking at how right they are. So there should be a difference between the low frequency events and the high frequency events. So if I ask you to guess how likely the lottery is versus how likely you are to lose your keys, okay, the lottery is a very low frequency event, and then if you're me, losing your keys is a very high frequency event. So they should have different ratings. I would say the lottery is 1 in 14 million, depending on what state you're living in. And me losing my keys at least once a day, so the frequency of that event is approaching 100%. And so if I were to look at the means for these numbers, which we'll do here in a second, I should see that they're different, because that is the whole point of the study. So this is kind of just a check to make sure the study went like I wanted it to. And then the next piece is the backward strength main effect. It's also significant. So 1 and 157. Oops. So BSG here 157 is 378.40. My p-value again is less than 0.001. And partial eta squared is 0.71. Now on this one it's tricky. So backward strength is something we tell people to ignore, so don't ignore the flip events. Right, so don't ignore. Ignore the flip events. So yes, sirloin to steak is really high, but if I'm asking you about steak to sirloin, you've got to ignore that. And that's tricky to explain to people. It's basically ignoring the likelihood of the events in reverse. And people are not really able to do that. So if we were perfect at this task, this would not be significant. But it is. So we'll see what that's doing to our ratings here in a second. And then let's look at the interaction. So again, it's 1 and 157. So one thing I want you to notice is in all of these, I'm pairing them together. 157 is this F number. 157 is this F number. They just happen to all be the same. Okay, so 157 is this one, 70, 99. P-value is still less than 0.01. And my partial eta squared that I actually used to estimate the power for this one is 0.31. And that's still a large effect size. So we got big effects going on here the entire time. So I have 3 significant effects, 2 significant main effects, 1 significant interaction. Now, let's see what happened. So I'm going to keep scrolling through my output. Next thing you'll get is within subjects contrast. This is if you're wanting to look at the linearity. If you have more than 2, this would make sense. But for 1, it doesn't make a whole lot of sense. I'm sorry, for 2, it doesn't make a whole lot of sense. But we could talk about if this is a linear trend going up or linear trend going down. But I don't want to, so I'm going to delete this. Here is my useless between subjects box. You get this box because some of the degrees of freedom and some of the error and some of the sum of squares are calculated here. Because you'll notice that in your between subjects analyses, you'll get totals and intercepts and corrected totals, and you don't here. Actually, the total always gets hidden from you. It's like back in Magic Land in the background. So you get this box because it's trying to tell you, oh, by the way, here's the extra power that you got, essentially, by taking out the error due to people being repeated. But for the purpose of understanding the output and going to a write-up, this box is useless. Okay, the next thing I've got my marginal means. Remember, marginal means are the scores in the edges, in the margins. So each variable one at a time. So for FSG, I'm going to stop and interpret what's going on. I've already talked in some of my other videos about how if there's an interaction, you will often ignore the main effects because that will save you type 1 error and give you some power for those main interactions. But when there's only 2 levels, you've already run the analysis, you might as well interpret it. But remember that if I have an interaction, I am of the belief that you can often ignore the main effects because the interaction was the important part. Some people argue you should still run the main effects post-talks. I don't know that it's wrong either way, but if you run the post-talks for everything, you should probably correct them in some form just to save yourself some type 1 error problems. Okay. Alright, so FSG, what happened? Well, I got my means here, but it looks like low is lower than high. Here's my problem. It gives you these little numbers, FSG1 and FSG2. Super annoying. There are labels out there in space. Why didn't it give me the labels? Well, it's because it doesn't know what to do with them. And so you have to remember, or you can go back up here to your factors box and look at what 1 and 2 was. So FSG1 is the low, FSG2 is the high. So the low frequency events, or pairs that were supposed to be rated low, are rated at about 53 points. Pairs that are supposed to be rated high are rated about 71 points. The average for these is like 20 and 80. So people are really doing bad at the bottom, but they're getting close to the ones at the top. And so for me, in this particular experiment with the hypotheses that we had, this was a good indication that at least they could figure out that some of them were low and some of them were high. They weren't just rating everything at the top. Now for BSG, you see a smaller difference. That's why the effect size is a little smaller, so about 10 points instead of 20. But for BSG, it shouldn't matter. So for low BSG, there's high and low forward strength, and we're asking them to not do that. We ignore that. Stop it. And so it's interesting to me that I still get this significant effect because you shouldn't, because they're supposed to ignore it. And so what that implies is that when BSG is high, people are cranking up their ratings even higher. So when the likelihood of the events in the reverse are high, you think it's going to happen even more. And so this is an important difference. So low is rated lower than high, but if I were to talk about writing this up, I would say the difference for this is only about 10 points, so it's not as strong as the first one. Okay, and then lastly I have a significant interaction which I have to figure out how to analyze. So I've got my little means box here that tells me the condition means. But I'm going to use my plots to figure out what I want to know. So I've got my low and my high forward strength, and then my low, my high backward strength. So I could analyze these two to each other. So if forward strength is low, what happens with backward strength? If forward strength is high, what happens with backward strength? Okay. I could analyze it the other way. So if backward strength is low, what's the difference between the forward strengths? And if backward strength is high, what's the difference between the forward strengths? In this particular study, what I was interested in doing is looking at holding one of them constant. And so to match the notes, I'm going to do this one. So if forward strength is low, what happens when you compare low versus high here? Because if forward strength is low, there should be no difference between these two. And if forward strength is high, there should be no difference between these two. And what we're going to show is that by adding in the backward strength component, we're going to get a kick from low to high. So there's going to be this space here, and the interaction is because the space here is larger when it's high as opposed to low. Okay, so basically the space between this blue and green dot is not the same as the space between this blue and green dot. Okay, and that's what makes it an interaction, is they're not perfectly parallel. So that is either going to be across or down, going back to my idea of how to analyze interactions. And so what I'm going to do is go down on this graph. If forward strength is low, what happens with backward strength? If forward strength is high, what happens with backward strength? So let's make our table. So we got mean 1, mean 2, P, D, and explain. God bless Word for capitalizing those for me. Alright, so if, let's see, we're going to do if forward strength is low, so FSG low, let's look at backward strength low, and then if forward strength is low, let's look at backward strength as high. Remember, one of them has to stay the same, the other one has to change. And then the other combination, if forward strength is high, backward strength is low, and then if forward strength is high, backward strength is low. High. JK. And so what we're doing is we're looking at what happens in the changes for backward strength holding forward strength constant. So to do that, I need some dependent t-tests, because dependent t is for repeated measures designs. So I'm going to run 2 dependent paired samples t-tests to analyze this interaction. Now let me go ahead and fill in my means and standard errors here from this box. So I got FSG low, BSG low, it's 50, 28. And we're going to use SE because that's faster to type. And then we got the mean is FSG low, BSG high, 55, 97. And then here I've got the mean is 64, 34. And standard error is 0.99. And then my mean here is 7790. SE is 0.94. Okay. And that'll help me when I go to do mode. Apparently I didn't feel like doing equal signs. Since this is going to be a dependent t, I'm actually going to have t degrees of freedom and p here. So not just p, because it's not one of those post-hoc corrected boxes. Okay, I've got to run it myself. So let's run that. So I'm going to go analyze, compare means, paired samples. And I just have to make sure I match what box I'm doing here. So low, low, so low, low. And then I want to do low, high. So low, high. And then high, low. and hi. So just make sure that your variables here are lined up to these variables here. So what I get is, why did it only give me one? Low, 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 high. All right, sorry, I must have done something wrong. 1 second. Okay, didn't like that. So, and then I'm going to do high, low, and high, high. Right. Okay, I must hit the wrong button because I didn't get both. There's both. So it's going to give me the means and standard deviations and standard errors again. So I could have made this box with just this here, so you can use that for moat. It also gives you the correlations between the two time points, which unless you have a very specific hypothesis for that, you're not going to use. And then here's the box with all the action. If you wanted to, from moat, you could also use these means and standard deviations here for d-diff. Cohen's D. If I wanted to do D averages, I would need the numbers up here. And we'll put both of them on there. But right now I'm interested in T. So my first T has got 157 degrees of freedom. And ignore the capitalization. Word does that automatically. Okay. And that's equal to negative 12.10. And our P is less than 0.001. For the second one here, I've got 157 is negative 1616, P less than 0.001. Okay. So they're both negative. Let's put explain here. So for the low variable, it's lower than high. And then here, the low variable is lower than high. Now, that doesn't seem like much of an interaction when they're doing the exact same thing, because the point of interactions is that they're doing different things. So here I'm going to look at, and it's about 6 points. And then here, the difference is about almost 14 points. I just subtracted them. And that is why there's an interaction, because the differences between the two are not the same. So we get this sort of fan effect. But it is much stronger to make that argument if I have differences in effect size. So let's talk about the average. And then I'll also add in here d-diff. Let me pull up moat. So for d-average, I'm going to go to Measures, and then Cohen's D averages. And this is where you have to enter all the means, standard errors, or standard deviations, and in. So I'm going to go 50, 28, and 5597. And then I have standard error, so 1.01, 1.01, awesome. And then be sure you enter in. It's going to give you D here because we couldn't have it dividing by 0, so there's at least 1 in there. But be sure you enter in because otherwise it's incorrect. So 158. So degrees of freedom is 157. Okay. If you do it this way, the T statistics will not match, so don't look at it. But Cohen's D is negative 0.45. So a medium effect. Let's do the other one. Okay, so I got 6434 and 7790. And then standard error is 0.99, 0.94, and N is already correct. And Cohen's D is 1.12. So a large effect. And that is the interaction. Differences in the effect size because the patterns are the same. So anytime you have the explanation where the patterns is the same, one is low, one is high, one is low, one is high, look at the effect sizes because then that's when the interaction will appear. It'll be that they're differences in strength. Let's also try d-diff. So over here in moat, I'm going to go to Measures and d-diff. Now, I could enter the mean differences from SPSS down here. This mean is standard deviation. Okay, so mean difference is negative 0.569, and the standard deviation of the difference, 592, and then always in, 158. So that gives me a Cohen's d of negative 0.96. And then this time the t-values will match. It's pretty close. Okay, I didn't enter a whole bunch of decimals, that's why it's not perfect. And then I got negative 13.56. My standard deviation of the difference is 10.54. And I got the right n going here. And that gives me Cohen's d as negative 1.27. So again, they're not the same. Okay. Now on this screen, you could actually calculate the whole thing from t. So I could enter 16.62. That would give me, slight differences in decimals. I always tell people to calculate from the means and ends the standard deviations if you have them, because if you were to calculate from t and independent t, your number is going to be biased, because the calculation when you only have t for independent t is not as good as a calculation with means and standard errors. Standard deviations, because of pooled variance. So I've always sort of made it a rule to talk about always do this from the means, because you have them, because it's your study. If you're doing a meta-analysis, you could end up doing it from t, because that's all you have. But if you have the numbers, enter them, because that will be more accurate, more appropriate than doing it from t. But in this particular case, they're going to be exactly the same. So that's how you calculate effect size. Either effect size is appropriate. People argue that dependent D averages is a little better at estimating the population numbers because D diff tends to overestimate. I argue that it could be either one because D diff matches the test statistic, aka T, how T is being calculated. As long as you're clear which one you're using, no big deal. Now, the very last thing is going to be this chart. SPSS does not handle doubly repeated anything very well. Okay? It's sort of awkward to run these tests. It's also very awkward to make any type of graph. And so honestly, I'm going to tell you that Excel is going to be your best bet to create these graphs in a pretty way, or R. But if you're doing R, you're probably not watching this video. So I would highly recommend working on this in Excel, or if you're not very good at Excel, there are so many YouTube guides on Excel, or you could watch the end of the ANOVA video, and I'm going to show you how to create the graphs for ANOVA, because it really will not do them in Chart Builder in SPSS for those particular designs. So you could watch one of the next videos to get a how-to. So let me show you the cheat way to do this in SPSS. It's not totally appropriate, but it will get you something sort of good enough for most purposes. So let's go to Graphs and Chart Builder. So there's two ways to do this. This is the easy way. So I'm going to click on Simple Bar. Even though I have a double design, there's just no way to use the cluster bar graph with the way the data is currently set up. Okay? So I'm going to highlight all 4 of these and then drag and drop them into Y. Okay, it's got to go into Y, you can't put it into X. Hit OK, and it will create me that fake index variable for X like we saw before. Over here, under bar graphs, I'm going to click Display Error Bars and hit Apply, with the warning that this is incorrect. It does inappropriately calculate error for these things. It overestimates because it assumes that each column is a different group of people, so it calculates it as if it were independent T, and that's why I'd probably recommend Excel, because Excel doesn't make that assumption, because it makes you enter the actual standard error to put in the error bars. Andy Field has a really great how-to guide in his book on how to fix this problem in his SPSS book, and it's probably somewhere on his website as well. It's statisticshell, all one word, .com. If you're interested, he's got tons of videos as well. He's awesome. Anyway, so I can drag and drop and put them all in here. Now the problem with this is that it's going to treat it as if there was one giant variable, which is no good, but what can you do? So let's click X-axis, enter, and let's give it a label. So this is going to be both forward strengths, and backward strength combination. Okay, because it's not just one variable, it's actually both at the same time. So you hit apply. My y-axis, which it gives me the loving label of mean, useless, is going to be the average participant rating for these pairs. And I'm going to force the axis to be 0 and 100 because that is the min and max for my particular data. Hit apply, and let's hit OK. And so here's what I mean about it not being perfect. Because if it were a good graph, these two would be stacked together. And then these two would be stacked together, and we'd have a little legend up here. But it does show you the differences between them, and what you could do is color each one a separate color. That would kind of work. Or you could learn how to use Excel, or you could kind of cheat in SPSS to make you give you the right graphs, although the error is still miscalculated. Okay. So let me kind of show you this cheat. And it really requires you to dismantle and remantle your data, which is why I don't really suggest it. And I'll give you an example. So what we could do is take the data and rearrange it. So what I'm going to do is copy it out here. Let's see. I'm really interested in forward strength, so I'm going to do low and high. Well, I'm going to try to copy it. See what it does. There we go. So I'm going to call this variable FSG low and FSG high. I'm also going to make myself a fake variable here that's BSG. So I'm going to rearrange the data to be an independent test, essentially. And so what this is going to do is it's going to force the data into an independent test, which is not how you'd want to run it at all, but it's a good cheat to making a graph. Okay. So I'm going to rearrange this. Go here. Now I'm going to take these two here, where the BSG is high for both of them, but low and high for FSG. And I'm just going to paste them down here and call this high. So I'm sort of pretending that one of the variables is independent. Okay. So now our error terms are still not right, but if you follow the directions for how to correct them in ND field and then use those variables here, they would be correct, I believe. So I'm just kind of showing you how you might fake SPSS into giving this to you. Right. So now let's do graphs and chart builder. Okay. I forgot to give my variables types, so I'm going to go in over here, and it didn't like this one, so this is a nominal variable. There we go. So graphs, chart builder. Okay, sure. Do your thing. There we go. Reset out here. So now I'm going to do a clustered bar chart. I'm going to take my BSG variable and put it into set color because it is a nominal variable. I've sort of faked it. I'm going to take my two FSGs and drop those into Y because it's the only place I can put two variables at once. Come on. There we go. It's going to create me this fun index variable. Now you can flip-flop these. So if I want a BSG on the Y-axis, I could flip them around. I want BSG, in the legend up here. And then the other one would be the X-axis. I want to display my error bars. Under my X-axis, I want to give it a label, so forward strength. Under Y-axis, my unhelpful title, so average participant score, rating. There we go. I got 0 and 100. Apply and go. So, if you'll see, this is the exact same graph I have up here, but now stacked together in a more appropriate way. So this would be a better graph for for a doubly repeated design. So it's kind of a way to make SPSS do it for you. Or you can use Excel to get this sort of appropriate graph. You'd still need to fix the error bars. And then that is it for doubly repeated designs.